There will be a cocktail later today. I mean, it's supposed to last 2.5 hours or something, according to the schedule. But I don't think it's going to last that long. But anyway, you're all invited. Well, before that, of course, we have a talk by Fabio Martinelli from Roma, and he'll be talking about this model in D dimensions.
Okay, thank you, Roberto, for the invitation. And so this is, maybe it's a little bit too loud, no? No, it's okay? Yeah. So this is joint work with Paul Clebon in Warwick and Alessandra Fagionate in the First University of Rome 1. Okay, so let me give you straight ahead the model. We will look at it. So this is a spin system, simple spin system, like the one I was of the same flavor of the one I was suggesting in describing in the open problem session. So I will describe it on Z2 just for simplicity. So attached to any vertex you have of Z2, you have a spin, conventional spin, which is either 0 or 1. And the chain goes as follows, that with rate 1, to each spin, a new value is sampled from the Bernoulli law, which assigns probability P to 1 and Q, which is 1 minus P, to 0. Okay? Then the new value is accepted only if in the southwest neighborhood of the spin that you are trying to update, which is this one. So if here you see at least 1 0. Okay? So first of all, the message is that the value 0 is the facilitating value for the dynamics. And certain moves are rejected, not accepted, if a constraint, namely if you have 2 1s here in the southwest neighborhood of the vertex you are trying to update. Okay? Other than that, the dynamics is very simple. Namely, if you do an update, you do an update according to an independent coin toss, which doesn't look at the rest of the configuration, at the past history or whatever. Okay, so the motivation is in the one-dimensional version. So in the one-dimensional version, so there is no southwest neighbor. There is only the west neighbor or east. Okay, so conventionally this is called the east model because originally it was proposed by looking at your east neighbor. Okay, in any case, this is a prototype for a constraint system showing glassy dynamics. So this is jargon from physics community. So glassy dynamics is really the dynamics of real glasses, window glasses. Okay, and there are several features that are sort of shared by this kind of simple Markovian evolution. In particular, there is a broad spectrum of relaxation times. There are dynamic heterogeneities, which means that in the space you see region where spins are changing rapidly, other region where spins are essentially frozen. Okay, and this this landscape of frozen, inactive, and active region change slowly with time. This is characteristic of liquid that are cool very fast and are becoming glasses. Okay, so of course the value of the parameter P or Q is important, and we will see that the regime which is interesting is Q very small, which correspond in physics to low temperature. Okay, but here we are not really concerned with the physics of the model. So now, so while this model has really, so the one-dimensional version has really a rich structure, also mathematically, so it involves some interesting combinatorics, touches other branches of probability, for example, random walk on upper diagonal matrices, some nice work by Yuval Perez and Alan Sly. So the D-dimensional version in D equal 2 or 3 is really supposed to play a key role in some realistic model of glass formers, and this has been strongly suggested by the group of David Chandler, is chemical physicist in Berkeley, Juan Garran in Nottingham, and co-workers. Okay, so, and it seems that some non-rigorous conclusion which appear in the physical literature about the way these processes, they reach equilibrium, which are the correct equilibration scales, so in our language would be relaxation time or mixing times, or heating time or certain set, are not fully justified, and some surprises came from a mathematical analysis. So in particular, some of our paper, they also have a physics version which appear in some physics journals. Okay, so let me first describe some facts about this is process in the dimension, say 2 dimension. So the infinite volume process is always ergodic and reversible with respect to the product measure, which gives probability P to 1 and probability Q to 0. That's so reversibility, detail balance condition is very easy to verify. Okay? Ergodicity, so ergodicity means that in particular in this case there is always a positive spectral gap, even in infinite volume. Okay? And so I will discuss that later. So if you work not directly in infinite volume but in a finite region, which could be either a finite region or a subset of the infinite lattice, there are of course irreducibility problems, because for example in a finite region if you start with only ones, then nobody is able to move. Okay? So you need some places where it's possible to inject zeros in the configuration and start the dynamics. Okay? This problem is solved, for example, using boundary condition that I will describe in the next slide. Okay? So boundary condition, if suitable, they restore ergodicity. And so the last fact is that whenever the boundary condition restores irreducibility, then there is a positive spectral gap. So a finite relaxation time. There is no inverse here. Okay, so spectral gap is the inverse of the relaxation time, just to keep the, So boundary condition. So throughout all the slides, green, the color green means 0, color red is 1. So the green are the good guys who sort of speed up the dynamics. And so whenever I draw a square with a color, this means that there, on that side, the value of the spin is frozen to either green, namely 0, or red, namely 1. Okay? So for example, if you have a box which are these white vertices, then I can put around, I can imagine that around, for example, this corner of the box, you have frozen zeros. Okay, which means, for example, that this guy has in the southwest neighbor 0, so this guy is able to move. This guy also is able to move because the south neighbor is green, and so on and so forth. So all these white guys are unblocked, are completely unfrozen, while inside, of course, they have to verify the constraint. Okay, so in this situation, I will refer as maximal boundary condition. Of course, there are also minimal boundary condition, namely the boundary condition that are sort of the smallest one that guarantee irreducibility. And this is necessarily, you need that the leftmost, southmost vertex with this guy here must be able to flip without any constraint. So you can imagine that, say, to the left there is a green little square, and all the rest is blocked, so is 1, okay? So this guy can flip only once this guy has flipped, and so on and so forth. Okay? So those are of course there are intermediate boundary conditions that that interpolate between these two extreme cases, okay? So there is some monotonicity in the relevant quantities, so it will be enough to understand, say, this case and this case for the quantities we will be interested. So I'll try to explain this picture that for us remains a challenge, okay? So this is the positive quadrant, and this is a simulation done like that. So there are minimal boundary conditions. So the origin, this vertex here, is the only vertex that is unconstrained, so it's free to flip, okay, just by tossing a coin. And the initial condition for the simulation is all ones. So initially, the first spin to flip is the origin, okay? If the origin puts a 0, then maybe a next spin is able to become, to change value, so from 1 goes to 0, and then there is like an avalanche, okay? And so the colors here are, so we record all the vertices that have been updated at least once within the time of the snapshot, okay? And the darker the color, the more times a vertex has been updated, okay? So in particular, all this white area has not been updated up to time t, okay? And so first of all, you see immediately that there is like, so, well, there is a symmetry along the diagonal, this is the natural symmetry induced by the constraint, because it's the southwest neighbor, okay? And the dynamic seems to be faster along roughly the diagonal, okay? And so I don't have the movie here, but if you do a movie in time and you rescale this set by 1 over t, the time, okay, then you get that the shape of the set more and more as t goes on resembles a well-defined convex shape, okay? So there is a conjecture that eventually there is a limiting shape for that, okay? So, okay, we have partial result in that direction. It's still very much open. And so physicists were interested in that because they think that this could be related to the way a glass melts, okay? So here is a little movie at Q extremely small. So the red region is where, sites that have been updated. The yellow are the actual minus 0 that you see here. You see that there is like a, I don't know, like a little bit like a tree structure, okay? But what is pretty clear from this movie is that the zeros, they are helping each other in really using the 2-dimension available. It's not really something that goes like an oriented path only, okay? But there is cooperation between different attempts in any direction, okay? That puts sort of anchors from where the dynamic starts again, okay? Okay, so let me give some general observation. So these are sort of the easy observations. So the Is model on ZD is less constrained than an infinite array, say in 2 dimensions, an infinite horizontal array of Is model, simply because so the true constraint here is that you have to look at these two guys, whether there is a 0 here or there in order to move. And I say this is harder than to just look to the left neighbor, only in the horizontal direction. Certainly, this is more the second model is more constrained than this one. So the second model should have, for example, a larger relaxation time, and this indeed is actually true. Sorry? Now, on ZD, there are no boundary conditions. So I just say that, on ZD, this is less constrained than an infinite array of independent one-dimensional East model. And therefore, immediately you can conclude that the relaxation time on ZD is less than the relaxation time on Z only, okay, for any dimension. Okay? However, this is not sharp. Okay? This is not sharp, and we will discuss that carefully. Okay? Now, in a box with maximal boundary condition, namely on the left side and on the bottom side, you have all frozen zeros. Exactly the same statement holds. Minimal boundary conditions are more tricky because minimal boundary condition, you have a unblocked vertex only at the, say, the southernmost leftmost vertex, say the origin. Okay, so you have to argue a little bit differently. And so this is the first so this is the first result, okay? So if V is a L by L box, then the relaxation time in this box is bigger than the relaxation time in one dimension on one side only, and less than the relaxation time on, say, the sum of these two sides, okay? And so let's see the arguments of the upper bound. Yeah. Well, it's the same. Oh, well, okay. Yeah, just the same. Okay, so consider, so the proof goes like that. So consider a directed spanning tree that is blue, rooted at the origin. Okay, so I just draw one possible one. And then on this spanning tree, you define an is-like process with the following constraint. So the root is free to flip. Okay, this vertex was free to flip also here. Okay, and any other vertex on the tree can flip if the ancestor is 0. Okay, so there is like an orientation given by these arrows. Okay, and now the East model on the spanning tree is more constrained than on the box because you are cutting certain edges. Okay, and therefore the relaxation time in the box is smaller than a relaxation time on the tree. And then in 2009, we proved with Cancrini, Roberto, and Cristina Toninelli that on a tree, the relaxation time can be bounded by the relaxation time for the one-dimensional East model on the longest branch. Okay, so that's it. Now the lower bound is very simple because if you have a minimal boundary condition, so maybe let us use this picture. If you have minimal boundary condition and you just look at the marginal of the dynamics in this direction along the x-axis, this coincides with the East model, and therefore the relaxation time of the full process must be at least the relaxation time of the East model on these vertices. Okay, so that's the proof. Okay. So now let me describe a very appealing heuristic for the relaxation time on the whole lattice, okay, which was the heuristic used by physicists. Okay. Now the interesting case, first of all, is when there is a very low density of the facilitating side, namely Q is very small. So write Q as exponential minus beta and then this correction, and beta is very large. Beta is like the inverse temperature. Okay? Now, in 2 dimension or in D dimension, at equilibrium, vertices, zeros, vacancies, they are a typical distance which is 1 over Q, so the D root of 1 over Q, so exponential of B over of beta over D. Okay, that's the typical distance between zeros. And then physicists, they assume that equilibrium is reached using a quasi one-dimensional behavior over a distance scale, which is just this scale here. Okay? And so therefore, they argue that the relaxation time for the full process in ZD is like the relaxation of the one-dimensional process over a finite distance, which is just the mean distance between consecutive vacancies. Okay? Okay, so they argue that. That's very sort of reasonable to believe. And okay, so so with Paul and Alessandria, so last year we computed the relaxation time with high precision. So in particular, the outcome was the following: that if the L is of the form 2 to the n, actually slightly more general than that, okay, then the relaxation time of the one-dimensional model takes this form. So if L is below exponential to the beta, is exponential beta n times and factorial 2 to the minus n choose 2. And then there are lower order. Okay? As soon as L becomes bigger than that, then this estimate becomes saturated, so doesn't change anymore, okay, apart maybe from a multiplicative constant. And so this is the correct expression for the relaxation time. Okay? Now, okay, so we know that we should use L, which is just as this expression, and therefore, if you plug this, I mean, in this formula, you plug the correct formula for this quantity, you get this asymptotic, okay, for the relaxation time in D dimension, but this asymptotic is wrong, actually, okay? So if it is wrong, there is only one possible explanation, that this quasi one-dimensional behavior is false. It's not there, okay? So really, the system evolved in a cooperative two-dimensional or D-dimensional way. Okay, so the theorem is instead is that the relaxation time goes like the relaxation time in one dimension to the power 1 over d, and so dimensional effects are important. Okay, so that's the so the proof. So there is an upper bound. I mean, there are all possible kind of techniques that are combined together in a rather complicated way. But so the upper bound is via renormalization group ideas, okay, which are sounds complicated, but in a sense it is not. And physicists, they didn't object using this word, okay. And lower bound instead is using the usual technique of finding a good bottleneck in the configuration space, and the bottleneck is constructed algorithmically. Okay, so I'll try to describe that. Okay, so first I will describe this renormalization group technique for the upper bound. Okay. Okay, so a key tool is a well-established and respected technique, namely when you have a spin system evolving with kind of a Glauber dynamics, it's a good idea to do block dynamics, namely to invent an auxiliary chain in which instead of changing one spin at a time, you change a block of spin at a time, you control better the blockchain, then you use Saloff-Coase-Diaconis tools to compare the two chains, okay, and get information for the original one. Okay, that's the grand scheme. Okay, so here we introduce what we call knight chain from the game of chess. Okay, so a knight moves, say 2 down and 1 left, or two left and 1 down, for example, or of course also 2 up and 1 right. Okay, and so this white stuff is the original two-dimensional lattice. So these gray blocks are blocks of certain size. Okay, I'm not specifying the size now. Okay, and we invent an auxiliary chain which has the following: that a Poisson clock of mean 1 rings is attached to each block. When, say, there is a ring at block A, so block A goes and checks the state of block B and C. Okay? if in B union C there is a 0, then the block A is updated just by putting IID values according to the Bernoulli measure PQ. Otherwise, the block A doesn't do anything, and you wait for a next ring somewhere else, and you proceed. Okay? So this is the night chain. So instead of looking at your southwest neighbor, okay, you look at this sort of southwest night kind neighborhood. Okay. Now, really, the night chain consists of 3 independent copies of the east-like blockchain. So here, so these 3 copies are drawn in different colors. Okay. Yes. Yeah. I guess so. Yeah. So, for example, there is the red guys, not the green guys, and the white guys. So a red guy will always check the state of red guys. The green, they will check the green, and the white, the white. Okay? So they don't talk to each other. Okay? And, each one is actually isomorphic to a chain in which there is a block A. The block A check whether in B or C there is a 0, and then goes to equilibrium. It's refreshed with equilibrium. Okay? And therefore, so the night chain is really a block version of the original process. Then there is some computation, really is an L2 computation, that says that the relaxation time of the night chain is the relaxation time of the our original chain, but with a different Q, okay? So it's an effective Q, and this effective Q is the probability that you see a 0 in a block of size little l, which is, of course, this expression here. Okay, is 1 minus p to the volume. Okay? Okay. Then there is a second result that makes a comparison between the spectral gap or relaxation time of the original east chain in 2 dimension with the night chain. Okay? And the result is like that. So the relaxation time in, say, Z2, okay, so there is some constant, times the relaxation time of the night chain. And then in front, well, let me explain with the picture here. So in the night chain, this guy goes to equilibrium with rate 1, provided that here or there is a 0. So how many steps of our original chain we should do in such a way that a 0, say, in B is able to induce equilibrium in A? Well, roughly, you could imagine that is something like the relaxation time of a region of size, say, 3L by 3L, because here there is a 0, which acts as a good boundary condition that induce equilibrium. Okay? So, of course, this is, heuristic. You have to prove that. But, so this is this conversion factor. Okay? So, you compute the relaxation time of the block, and then you have to pay something, and typically this is the relaxation time of one single block, provided that you have a good boundary condition close by, which is there. Okay? And so if you put together all this estimate, what we end up is the following. So this night chain is the original one, but with a different Q. Okay? So you end up proving that the relaxation time with parameter Q is bounded by the relaxation time with this effective Q. Okay? But the same quantity, so with just a new Q. And then there is this quantity here. This quantity here, actually, we know very precisely because it's a one-dimensional computation, and we know the very precise asymptotic of this function. Okay? So, and we know that in any case, this quantity here that we are trying to estimate precisely is bounded by the one-dimensional quantity. So it's like a starting point from for some computation. Okay, so in a sense, at the end of the day, what one proves is a functional inequality of the form that the relaxation time with parameter q is some explicit function of q and the size of the block times the same quantity with this new q that depends on L. Okay, and this function is rather explicit. Okay, so this you solve. Okay, and okay, so here is the solution. So you imagine that this quantity is smaller than this quantity here. We want to get to lambda equal 1 over d just to prove our theorem. Okay? Initially, you know that lambda is only less or equal than 1. Okay? And then using the function inequality, you prove that if this is true, then the same inequality must be true with the new lambda, which is given by this expression here. Okay? And this map here has an attractive fixed point at value 1 over d. And so you iterate this renormalization procedure until you get to the fixed point, which is 1 over d, and you prove the upper bound. So, yeah.
So the reason that you can justify these values is when you're moving up a bound, you're just essentially slowing down the boundary, ignoring other people nearby who can kill you.
Yeah, roughly. Yeah, absolutely. However, I mean, if you are working on length scale that are less than the average mean distance between zeros, it's not such a bad approximation because zeros are really isolated, right? So there is no too much hope of seeing other zero that can help you in a significant way, right? Yeah. So now, so lower bound is a completely different story. Unfortunately, we couldn't find a renormalization group argument for the lower bound. And instead, we use this bottleneck. So bottleneck works like that. So first of all, I mean, if we impose that on certain region spins are 0, so we freeze spin to be 0, then the relaxation time can only decrease because the system becomes less constrained. So we choose, guided by this intuition that everything should occur on this equilibrium scale, which is 1 over, say, in 2 dimension, 1 over root q. Okay? So we impose maximal boundary condition. And then we have just to lower bound the relaxation time in a finite region. And for that, we use the bottleneck inequality, okay, which is this one. Okay, so you have to find the max of this is like an isoperimetric inequality, right? Okay, so there is a little loss, okay, which is not very serious for our purposes. Okay, so the key point is to find a set A in configuration space such that this probability, so the probability of the boundary is very, very small compared to the probability of A or the probability of the complement of A. So that's very standard. And so, so there is a theorem that shows that there is actually a set with a bottleneck ratio which is so large with exactly the same factor D. Okay, and this will prove the theorem. Now the proof is an algorithmic construction that I don't know. To me, reminds a little bit of this recursive majority rule that was used, I don't know, 10 years ago, or maybe more, by Yuval Mossel and Claire, yeah, for the easy model on trees. Yeah, thanks. So the algorithm goes as follows. So imagine that you have a configuration of 1s, the red guys, and 0, the green guys. Okay, first of all, I define what is the gap of a 0. So unfortunately, gap here has nothing to do with the spectral gap of the dynamics. Okay, so I say that the gap of a vacancy of a 0 at xa is the L1 distance from the other zeros in the southwest direction or from the boundary. So for example, in this example, A has distance 1 from the boundary where there is a 0. So gap of A is 1. Gap of B is 3 because it's 1 plus 2, 3. And gap of C is 4, 1 plus 3. Okay? Okay, so the algorithm goes as follows. Yeah. Sorry? This one? Oh, you're right. Sorry. I was wrong. Yeah, thanks. Okay, so, I don't know when. Yeah, I'm always concentrated on, doing something that is not the most straightforward. Okay. Yeah. Okay, so assume that you are given in a box, you are given a configuration of 0, 1s, okay? Then, later I'll explain which is the intuition behind the algorithm, okay? So the algorithm goes as follows. First of all, you remove all the vacancies, the zeros of the configuration, which have the smallest gap, say 1, okay? You delete those, okay? And you, of course, so you replace with 1s. And of course, you end up in a new configuration. This new configuration, call it eta prime, okay? Now, eta prime has no zeros with gap 1 because I've been removed before, but maybe the shortest one now is 2. You remove 2. You get a new configuration, then you remove 3, and so on and so forth, until you have removed all gap up to L minus 1, and then you stop, okay? So you have a final configuration. How does the final configuration looks like? Well, because there are all zeros, frozen zeros around the boundary, the output configuration can only be of 2 types. Either are all 1s everywhere, or there is a single vacancy at the topmost, rightmost vertex of your box, because maybe that vertex there was at gap L, and we stopped the algorithm at L minus 1, okay? Good. So then the bottleneck consists exactly of all the configuration, such that when you apply this algorithm to the configuration, you output the configuration with a single vacancy in the topmost, rightmost vertex of the box. Okay? Okay, so this is a definition, okay? So this is a well-defined set. And of course, the problem is to prove that the bottleneck ratio for this set is exactly the correct size. Okay? Now, the construction, is not completely out of the blue, but is based on the following intuitive idea that if you run the dynamics starting from this configuration, so the system, Q is the density of the green guys is very small, so you try to eliminate green guys. So the first one to be eliminated should be A because it's as the closest distance to another green guy. Then you should eliminate B, then C, right? Okay, so this is more or less the idea behind this construction. And of course, the estimate that the bottleneck ratio is highly non-trivial because there is a horrible combinatorics behind it, but it comes out just nice, okay? And if you take the function that is 1 minus the indicator of this set A, this bottleneck set, is actually is a very good approximation of the Dirichlet problem, in which you have, this is the generator of the dynamics. You have, L is like a Laplacian, ideally, is 0, and with boundary condition, in all 1s you are 1, and on the set of configuration with the rightmost, topmost 0, you are 0. So if you try to solve these problems, namely you are looking for what is called the equilibrium potential for this problem here, okay? It's quite reasonable to imagine that this equilibrium potential will be almost like a step function, namely will be 0 on some configuration and 1 on other configuration, okay? And this capital F has exactly this property, and is a really a very good approximation of the true solution. Okay, so then so after the relaxation time, we went to analyze what we call persistent times, which are essentially hitting times, and the goal is exactly to try to understand this oval picture that I showed you at the very beginning. So the setting is the following. So take a, say, triangle, okay, with equal side, I hope. Let's see. Yes. Okay. And you start with all ones, so all red, except that there is a 0 on this diagonal. Okay. And you ask, and you measure how long does it survive. Okay. So these two green guys here will maybe make this green, then another green, and so on and so forth, until maybe a green comes here, and this guy will then become, most likely, if Q is small, will become red, okay? And this, and the guy is eliminated, okay? So we call, so if this is V, so that's the mean survival time of the initial 0 at this vertex. Okay, and so the main question is, so it's very tempting to say, well, the asymptotics as Q is small of this persistent time is dominated essentially by the L1 distance of this green guy from the source of vacancy, namely the origin. Okay. Okay, so. So there are, of course, we examine two different cases, which are sort of extreme. Okay, one case is when the initial green guy is along one coordinate axis, so case A. Okay, so in this case, the origin here must send like a wave of zeros along this x-axis to capture this green, kill it, okay, and go back, right? And to do that, along this axis, the dynamics is exactly like a one-dimensional East process. Okay? Now, in case B, instead, we place the position of this initial 0 is, say, exactly along the diagonal, let's say. Okay? And, well, the L1 distance is still the same, okay? Except that actually there are more ways to reach this 0, many more ways, okay? How does this extra entropy plays a role? Okay, so we will see that plays an important role. Okay, so the theorem is like that. So suppose that the L1 distance from the origin of the initial 0 at V is, say, in this range, but n is O1 as Q goes to 0. So n maybe is 100, and then Q goes to 0. Okay. Then really the L1 distance dominates the asymptotic of this persistent time, okay? And the persistent time scales like that, okay? So really there is like a quasi one-dimensional behavior. You just, follow a one-dimensional path in any case, okay, to capture that and go back, okay? Now, okay, so here I present the result only for these two extreme cases, when n is order 1, or when 2 to the n is exactly 1 at this critical length. But actually, we have a result for all intermediate, for all the range. Then actually, what we prove is the following, is that the persistent time in the diagonal direction coincide essentially with the relaxation time for the infinite lattice. And instead, over on the horizontal direction, in case A, this persistent times is much, much larger than the persistent time in the diagonal direction, because it's the persistent time in the diagonal direction to the power 2 minus 1 over d. Now, d is at least 2, okay? So this power here is bigger than 1. So really, the dynamics, at least up to this scale, proceed much, much faster along the diagonal direction than the horizontal direction. Okay, so there are dimensional effects. Well, by dimensional effect, I mean that the entropy, the entropy that we that we can exploit around the diagonal is very, very important. Okay, that's the. Okay, so some comments. So in one dimension, and so the equilibrium scales, namely the mean intervacancy distance, is 1 over q. Okay, when q is small. So we prove with Clebon and Fagionato that actually the relaxation time, mixing time, and persistent time, they are all within a constant one from the other. Namely, the ratio of any of the two is within a constant and 1 over a constant. Okay, for some universal number. Okay, of course, this is true only up to this scale, because for very large scales, much larger than 1 over q, okay, the mixing time must be at least like linear. Okay, and the relaxation behaves essentially like a constant, is order 1, so they are very, very different. But up to this scale, they are just the same. Okay. Now this actually is false in our dimension, because we just proved that on scale, the equilibrium scale, which is here was 1 over q in 2 dimension, is 1 over root q. Okay. Then the persistent times along the diagonal is much shorter than the relaxation time, which actually coincide more with the persistent time in the horizontal direction. So in a sense, the system is able to reach a point along the diagonal without having mixed elsewhere. Okay? So that, in a sense, explains the white region in the original picture, not this like egg-shaped picture. I mean, outside that, I mean, things were not updated, so certainly were not at equilibrium. Okay? So it's really a purely out of equilibrium process. I don't think that I have time to describe how we examine these persistent times, because since they are, very different from the relaxation time, we cannot exploit only L2 consideration, Dirichlet form and stuff like that, but really we have to find some non-equilibrium tools. And so maybe I can just say that the idea is to construct a resistor network in which nodes are the configuration of spins, edges are pairs where there is some positive conductance, okay? And we have to estimate the global resistance of this network. Okay, and this we do by variety, so using the Thomson principle, the Dirichlet principle, to get upper and lower bound on the resistance. So I would like maybe to conclude. Okay, open problems. Okay, so there is a list of open problems that really need to be solved, and so all these problems, I mean, and in a sense, are tied one with the other. Okay, so if one understands how to solve, say, number 1, most likely there are good ideas to solve 2, 3, and 4. Okay, so the first problem is the following: imagine that on the whole lattice you distribute your initial value for the process according to, for example, a product measure, but the probability of 1 in this starting measure is different from p, some other values, p prime. Okay, so it's a non-equilibrium value. Okay, then compute, starting from this distribution, the probability that at the origin you are at time t you are 1, and you would like to know whether this value, when t goes to infinity, converges to the equilibrium one, p. Okay? So if yes, how fast? Okay? So this still is unknown. Okay? Because we only know really relaxation time. Relaxation time is an L2 quantity. Here you are starting from like an infinite perturbation of the reversible measure. There is no chance that with an L2 quantity you can, prove that. So you need that extra tool. Maybe now we are on the right track. Okay. Now, second question is fix Q. So Q is not going to 0, nothing. okay, and estimate the mixing time in a box for large L with, say, maximal and minimal boundary condition. Does it depend on maximal, minimal boundary condition? Is there a cutoff phenomena for the process? In one-dimensional, we prove it with Shirshendo-Ganguly and Eyal Lubezki, that indeed there is a cutoff with optimal cutoff window. And so the question is whether there is still this cutoff here and whether the window is still optimal. Eyal is positive about that. Thanks. Okay. And so fix Q and show that if you compute the persistent time for very large L, namely you fix very far away, you fix an initial zero and you compute its average survival time, okay? You expect that this time scales linearly with the distance, L, okay? So this is certainly is related to this. And finally, maybe the most ambitious result is prove a shape theorem, namely prove that there is a limiting shape for this rescaled set of vertices visited up to time t. And so what we know now about this, so this shape was something like that if you really look carefully, okay? So these are the region, okay? But if you look carefully, there is a point, okay, where the shape detaches from the coordinate axis, okay? And now, along the axis, the evolution is just a one-dimensional evolution, okay? And in one dimension, we know that if we start with, on the half line, we start with all ones. At a later time, there will be a rightmost zero. Now it is known, this was proved by Oriane Blondel in 2013 or 12, that the rightmost zero proceeds to the right with an asymptotic velocity. And then with Shirshendo, Ganguly, and Eyal Lubezki, we also proved that the fluctuation of this rightmost zero are normal. So, so this guy here is like, if this shape is rescaled by t, this is really some known, of course not explicitly, constant v, okay? And the question is, what happens here, okay? So this we don't know. We don't even know that it takes only linear time to get to this distance, in a sense, so that the correct scaling is t, okay? So this is, of course, related to the mixing time, whether the mixing time scales linearly and so on. Okay, thank you. Yep.